Our goal in section 6.1 is to draw and use slope fields as an aid in solving differential equations. Remember that we solved differential equations in the section that we did previous to this by using antiderivatives. We had a derivative and we did the antiderivative. Well, we use slope fields. We use those when we cannot solve the differential equation analytically. There are different ways to find antiderivatives, therefore solving a differential equation. Analytically is the way we did it last time. Analytically meaning using the algebra, the calculus skills. So analytically meaning using the technique of separation of variables and then integration. Well, when we can't use separation of variables and integration because it's just too complex, or it lends itself more to a graphical approach, that's what a slope field is. So I'd like to show you first what is a slope field before I describe it to you. So this picture is not in your notes. I'd like you to just take a moment to watch and to listen and let it soak in. Here's a graph. We are going to, or I am going to, sketch little tangent lines at various points on this function. So for example, I'm going to look at the point 0, 0, and the slope here is horizontal. Here's a little point. There's the slope, there's a tangent line. Here's a tangent line. Here's a tangent line. Here's a tangent line. Once I have some of those, I'm going to remember about what a tangent line is. Represents the slope. Remember, the slope is the derivative of the function at a point. So this is the slope at 0, 0. This is the slope at 1, 1. Those are the slopes. I now want to, keeping those original tangent lines there, move the function, and I'm going to do it again. So I'm going to move this function down and draw these little tangent lines again. So I'm just trying to make a line that's tangent to the curve at those indicated points. And I'm going to grab a hold of this parabola and move it and do it again. And as I draw these little tangent lines that represent the slope at those points, what you're going to start to see as I do this over and over are a bunch of little lines that represents the slopes all over, depending on where my curve is. And when I move my curve out of the way, it's a field of slopes. It's a slope field. I've created a visual of what the solution would look like. Now let's go back to that picture of the parabola. You can probably guess in your head what would the equation of that be. So that red parabola would be y equals x squared. What's the derivative of that equation? Oh, I'm sorry. This one's y equals x squared minus 3. Let me put it back to where it was originally, y equals x squared. And now let me ask you, what's the derivative? dy dx. 2x. Now, let's say I didn't move it from y equals x squared minus 3. What's the derivative then? Still 2x. In fact, if I move it up to plus 3, what's the derivative? What's the derivative then? Still 2x. So really, it's any value that I want to add on, any constant value that moves my curve up or down, that's going to give me the same derivative of 2x. When we solved the differential equations analytically, we separated our variables. So we said dy equals 2x dx, and then we integrated and got y equals x squared plus c. Well, today we're going to look at what can we do when we can't integrate. So this is a slope field, a field of slopes. Now we just said that the derivative dy dx was 2x. If I look at a variety of points on the graph, such as at the point 0, 0, well, dy dx at the point 0, 0 is 0. Hence, the slope at the point 0, 0 is horizontal. The slope line is horizontal. The tangent line is horizontal. What about at the point 1, 0? Well, at the point 1, 0, dy dx is, well, 2 times 1 is 2. So that little line has a slope of positive 2. Okay, what about I move over to the right a little bit at the point 2, 0? So dy dx at the point 2, 0 is now 4, hence why it's a steeper line. And that's how we create a slope field, by starting with the derivative. Once we start with the derivative, then we can sketch in what the curve probably looks like and take us to perhaps that parabola of y equals x squared. Perhaps the parabola of y equals x squared minus 3. It could be y equals x squared plus any constant, positive or negative. That's a slope field. And that's how we use a slope field. So let's go back and write down what is a slope field. Now, sometimes it's called a direction field. Some places you'll see it called a direction field instead of a slope field. These are just, no matter what we call it, graphical representations of differential equations, so that we get a visualization of the parallel curves that will solve the differential equation. Graphical representation of differential equations gives us a visualization of the parallel curves that solve the differential equation. So this is a way to solve the differential equation graphically. Now, I took a moment to pause at the word parallel, because as we work through a slope field, that's what we're going to have to think of, is maybe we don't necessarily hit the point, but we want to be parallel. And that'll make more sense as we do some examples. I've drawn a slope field for you, and often you're going to see problems like this where it's already given to you, the slope field, and you need to use the slope field for the differential equation given. In this case, it's dy dx, or y prime, equals 1 divided by x being greater than 0, to sketch the graph of the solution that satisfies the given initial condition. First initial condition is the point 2, 0. So we go to our graph and we find the point 2, 0. There's our initial condition. Well, right on top of that point, I see a little tangent line. I'm going to trace right on top of that tangent line, right over top. Now, as I grow my curve to the right, I'm going to notice that there's no slope lines to be on top of, but below and above I have slope lines that give me the direction that I should be traveling. Just make sure that you are traveling parallel to those slope lines if you're not touching them. So here I'm touching one, here I'm not touching one, but I can be parallel, oh, really close. Here I'm parallel to that one, keep going. Now, one thing to remember when using slope fields as an aid for solving differential equations, it's an estimation technique. So it's not going to be a perfect solution curve. Now here it looks like the slopes drop off and I don't have anything left to graph. Well, remember that they said this is only for x greater than 0. So can you think about what type of thing graphically is going on here? They don't just disappear, but the way they are getting steeper as we move to the left, it probably means there's a vertical asymptote here. So I'm going to graph it as if there is a vertical asymptote here. That's usually what we're going to see when it's domain restriction like that. So I'm going to say probably a vertical asymptote. There's one solution curve. Do you want to try to graph the other one? The initial condition is 3, -1. How about you pause the video and see if you can do this one? Point starts there. Draw right on top of that solution curve, right on top of it. Just like that. As I move to the right, stay parallel to the little tangent lines nearby. As I move to the left of that point, stay parallel to the little tangent lines nearby. Unless I hit one, then I stay right on top of it, and then follow that such as it's a vertical asymptote. There we go. We have two different solution curves for two different initial conditions. Now let's go back to what we were doing last time, where we solved these using separation of variables. Now what we have right now, this guy right here, this is a general, this is a particular solution, but it's a graphical particular solution. This is a graphical solution to the differential equation that was given to us, y prime equals 1 over x, a graphical solution. Let's also show an analytical solution. That's what we were doing last time, an analytical solution where we started with dy dx equals, in this case, 1 over x. We separated the variables, so I have to move the dx to the other side, 1 over x times dx. Then we integrated. The integral of dy is y. The integral of 1 over x is natural log of absolute value of x, and I save my collective constant for the end. There is an analytical solution. Now this guy right here is a general analytical solution. If I want exactly what this one is in green, I'm going to now go to my initial condition of 2, 0, and I'm going to plug it in. So 2, 0. 0 is the y, 2 is the x, and it looks like c is the negative natural log of 2. So my particular solution is y equals natural log of absolute value of x minus natural log of 2. There's an analytical solution. Now I did say earlier that we use slope fields when we can't solve a differential equation analytically, but we're going to start with basic differential equations so that we can see the connection between what the general solution looks like, general solution, a natural log graph, and what the graphical solution and the particular solution that we solved analytically. Here is our general solution. I keep saying general solution. That's my general solution. There's my particular solution. What I just want you to really notice here is the way we solved the two. Graphically, it looks like a natural log curve. Analytically, it looks like a natural log curve. Do you want to try the next one? So two here for you to try. I'm going to go through these two a little bit quicker because there's a reason that I showed you two different ones. And I want you to really notice the differences between these two graphs. So maybe pause the video, do these two curves, see how you did. 2, 3 is here, and follow the little curve lines, looks like that. And 0, 5 is here. Follow the direction, and it looks like this. Okay. Let's practice solving this analytically. So we've got our two solutions. This is a graphical solution, or rather I should say these are the graphical solutions. Now let's look at analytical solutions. Solutions where we solve this by differential equations. So we'll start with dy dx equals 4 minus y. Separate means dy over 4 minus y equals dx. Then we'll integrate. integrate both sides. It looks like we're going to need a little u substitution here for the bottom, so we can say u is 4 minus y, so du is negative 1 dy, or du dy is negative 1. So I'm going to have an extra factor of negative 1 hanging out. My bottom is u, so that makes negative natural log of absolute value of 4 minus y equals, on the other side, that's x, and then a collective plus c. Now we want to get the y by itself. So let's first start by multiplying the negative to the other side. Natural log of absolute value of 4 minus y equals negative x plus c. I'm letting my constant just absorb any sort of coefficients, multiples, additions that come its way. Now I'm going to exponentiate both sides with base e. Exponentiate, exponentiate, base e. So I've got on this side absolute value of 4 minus y equals e to the negative x times e to the c. Remember, adding exponents means multiplying the common bases. Now I'm going to get rid of my absolute values and let the plus or minus get absorbed in the e to the c. So this guy I'm going to call just c, and then e to the negative x. Subtract 4, and then multiply again by negative 1. Again, my c is just absorbing those constants. So here's an analytical solution. An exponential function, right here, e to the negative x, but it's a negative x, so it is an exponential function of decay. Now I'm going to go with this second initial condition just because it's easier to use the 0 to make it a quicker example. So here's my general solution. Let's look at the particular solution with the point 0, 5. So 5 is the y, ce to the 0 is the x, plus 4. So e to the 0 is 1, so that doesn't really have an effect. C equals 1, it looks like. So plugging the c back in here, my particular solution becomes y equals e to the negative x plus 4, my particular solution. Well, e to the negative x, that's exponential decay, hence the pink graph coming down. Added 4 units to it, see our horizontal asymptote right here, 4 units above the x-axis. Normally an exponential function is like that, exponential decay. Well, this one is raised 4 units up. See the connection between the analytical solution and the graphical solution. Now let's talk about how to graph slope fields. Stay tuned in the next video.